Okay, let's start. Today we will talk about PCA, and because Barnabas has not finished his slides from several weeks ago, so I will cover kernel PCA for him, and we want to talk about randomized algorithm for fast PCA computation. So hope you still remember PCA. Is that okay? Okay, cool. So we can go very quickly. So generally you have PCA is that you have a very high dimension space data you want to reduce it to a low dimension space. So that is what PCA does do. Okay, and here's a Gaussian example. So because the basic assumption of PCA is that the data is quite usually on a very low structures, lies on a very low manifold. So even though we observe very high dimensional data, but maybe only a few dimensions has informations, and all the others are just a noise. So, but the data we observe usually has rotated, so we do not know which dimension contains useful information. But this is an example. So we first compute the principal components and the second principal components. So we can assume that the first principal components contains useful information, and the second just some small noises. So we can reduce that data into one dimension, and after rotate the data. So this is what PCA do. Actually, the algorithm is quite simple. You first compute the maximum gradient principal components and substitute that component, and then find the next one. So actually it has a very nice closed form solution that compute the eigen decomposition of the covariance matrix. So you first compute the covariance matrix and do the eigen composition. So you have n eigenvalues, number 1 to number m, and you find the top k principal components and get the eigenvectors. So that is PCA. And so if the data is centered, you can just do a SVD, singular vector decomposition on the x directly. So you have x here, and you compute x equals u times s transpose v. So both u and v are orthogonal. S is a diagonal matrix. Each diagonal entries contains singular values. So if we want to do a k-dimensional reduction, we just find the leading k singular values and find the corresponding singular vectors. So far so good. And so we jump. So here is the slide we will start. Oh, it is not a slide. Okay, so we will go. Okay, here's the slide. We will begin with that. So what is the problem with PCA? One problem is that if you have labels, PCA do not know the labels. Actually, it's unsupervised learning. So for example, in this case, you have two different kinds of data sets. One's yellow and one's red. PCA do not know that. So it just finds the principal components is this one, and find the second one. So if we want to do a one-dimensional reduction, you just keep this one. This is not what we want, because this is a direction. It corresponding to a hyperplane in that direction. So actually, we want to find a hyperplane that separates these two data sets. We want to do this one. So actually, what we want is that direction. So PCA do not know that. So here is if we using a Fisher linear discriminative, it's a supervised learning. It takes the labels, so it can find that correct directions. So on that direction, you have that. On this direction, the hyperplane, you can separate the data. So that is all true for, generally speaking, for supervised and unsupervised learning. If you have labels, you want to have supervised learning. If you do not, maybe you can try PCA. And so you add the cost, maybe you get something wrong. So if you do do the dimension to a very low dimension space, you get something wrong. And another problem is that PCA is a linear model. So the object function is not linear, but so the problem is linear. So it only finds linear structure of the data. So if this data structure do not have a linear form, it fails. So how to do that? It's a nature idea. So we go kernel PCA. So the basic idea is that use the eigenvector of the covariance matrix sigma, and actually use a linear combination of the samples. So we have the next form here. Actually, U can be represented by alpha I times xi. Xi is the I sample of the data. Alpha I is just a scalar, it's a coefficient. So remember that if you want to how to do kernel method, we just think that the thing we want to have is just a linear combination of the samples. Remember that kernel perceptron, kernel SVM, so it works as the same. So now we have linear combination of the component singular vectors. So next job is how to find the alpha. And because we only have inner product here, so because so we first show that. So how to compute sigma times U? If U is presented by a linear combination of xi, then after some calculations, we have that form. So we have that form equal to this one. So K is a kernel matrix actually. Kij is just the inner product of xi and xj. So we don't need to know what U looks like. We only need to find what alpha is here. K is a linear product of data. So this is how to compute alpha I. So we can solve this one directly. It's a linear system. You can just calculate the second decomposition, and we get alpha. Next question is that if we have a new sample, how do we project into a null space? So here T is the new sample here. U is the components we have. So expand that U, and that is equal to alpha j times the kernel distance between xj and the new sample. So even though we only know alpha, so we can compute the projected of the new sample T. Okay, so what's so good? And remember that the covariance matrix want to have the data is centered. So that is each sample has been minus the average ones here. So how do we do sampling the kernel thing? So it actually works. It's a trick. So okay, so because it's a linear kernel is a linear combination of the phi xi is the thing on kernel space. So you can minus the average as we done before. Okay. So what is kernel PCA? So first calculate the kernel matrix of the data and find the top k eigenvectors of the kernel matrix. So you are done almost. So if you can a new sample here, you just first calculate the kernel distance from this new sample to all the samples you have, and times the alpha here. So you get the projection. Here is an example. So for the original data we have nonlinear structure here. So it's a cycle here. So if we run PCA, it's get wrong because we do not know nonlinear structure. After polynomial kernels, we can span that space onto a linear separable case. So it works using linear PCA. Is that good? Okay, so actually it's simple. So here is something that show that you have two algorithms for PCA. First is sequentially compute the principal components and minus that term from the data, and then compute the next principal component. That is algorithm 1. And the 2 is that you have a data, you just compute the covariance matrix and do the eigen decomposition. So you get all the k directly, all the k component, principal component directly. So that is show these two are exactly the same. So you can. It's not very hard. Okay. So far so good. So let's move to the next one here. So we want to show how to perform a low-rank approximation of a matrix here. So given matrix A, here A is a n times m matrix. We want to form a rank K approximation by approximate A equals to P times sigma times transpose Q. So that how A is approximate A very well. And sigma here is a K times K submatrix. Usually we want to have K much less than both N and M. So remember that is what PCA does. So if A is a sample matrix, it's a sample by feature matrix, you want to find the top K eigenvalues to approximate that data matrix well. So this is what PCA do. So here is an example here. You have a large A, and we want to have only some columns, K columns here, a small matrix here, and K rows here. So we hope that this form approximates all the entries of A well. So this is rank K approximation. And why we want to do low rank? There are several reasons. So the basic assumption that it's very similar to PCA, that the data is quite often lies on the low dimension space, or we call manifold. And so you observe very high dimensional data, but not they are noisy. So actually the basic structure is quite simple. You have images, the board we have is a 3-dimensional plus a time maybe 4-dimensional. So maybe a low rank presentation approximate the data is very well. So if that case, we prefer a no complexity representations. And it has advantages for using no rank approximation. First is that denoising. You have noise and you remove some noising, and also it's a visualization. You have a very high dimensional data, it's not easy to plot that data. I mean, you can, if you reduce it into a 2 or 3 dimension, you can just plot it, as many standard software can do that. And the most important thing is that you can reduce the storage requirement. Instead of store the whole matrix n times m, so if you have n is 1 million, so it takes 100 gigabytes. So you can reduce the storage into n plus m times k. K is usually very small. So on that case, you can usually store a very large matrix on the memory. And it can reduce the computational complexity. For example, if you want to perform A times X, X is a vector. So the naive case, it takes O n times m complexity. You want to scan the whole matrix. But if you can present as a low rank approximate structure, so you can do that from. You first transport Q times X. Q is actually it's a very skin matrix, and times a very small sigma here, and then times a P here. So it can reduce the complexity to n times k. Given k is usually very small compared to n, so it saves a lot. And especially interesting that you want to do an inverse of A. So if A is not full rank, we use a pseudo inverse. So A plus is a pseudo inverse. So if P and Q are orthogonal, if not, we can do QR decomposition to make it orthogonal. So it takes n times k squared times complexity. And if it is orthogonal, so the inverse of A can be approximated by P times inverse of sigma times transpose Q. Sigma is usually K times K very small matrix, and usually it's a diagonal. So you can do the inverse very easily. On the naive case, you want to have n times m times the minimum of n and m. So actually, the constant here is very large. Usually 20 or between 20 or 100. So you have a very, that thing do not have a very hash locality. So basically, you run that is very slow. So on that case, basically you just do matrix multiplication. So it's quite simple. The time constant here is usually 2 or 3. So it's much efficient. Okay.
Right?
Yeah, you mean this term?
Yeah. Is it like, how do you get that?
Yeah. It means if you want to do inverse, it's usually if it's a standard thing. Sorry?
Do you only want to compute like 8 first times of that? So
Yeah.
if you want less information.
Yeah. If you only want to have inverse A times a vector X, you can just solve in a linear system. But it's not usually the case. If, for example, you do linear least square regression, you won't have a full reverse here, inverse here. So you cannot solve that. You want to have find the inverse directly. But usually it's not a case. Maybe you can use QR decomposition to get a better numerical algorithm, but the time complexity is here. You can reduce the constant here, but you cannot reduce the scale. All right. Yeah, it's what PCA do is just reduce the dimension, and because yeah, the basic assumption is that the basic structure of the data is quite slow. If you have millions of dimensions, it's quite okay. Maybe you can reduce to 1,000. Yeah, certainly you remove noise, and also you lose some useful things. Yes, exactly. And so here, what if you want to get rank K approximation? What is the best one we have? It's quite simple. We first want to solve this optimization problem. So, given A, given rank K, we want to find P sigma Q such that the error between A and P times sigma times transpose Q is as small as enough. So you can using the rank K approximation to prox A, very good. And the constraint here, sigma is a K by K matrix. So if sigma is K by K, so P has only K columns and Q also has only K columns. And this has a closed form solution. It just truncate SVD. What that means, what we done on PCA. If I steer a field from Barnabas, so here the matrix should be A. If we do a SVD on A, it can be U times S times V. So we just keep the K leading the biggest K singular values, and keep its corresponding singular vectors, and drop the rest of one. You can get a rank K approximation. And it turns out that it is the best you can have. So generally, if the eigenvalues has a power law distribution, that is true on most cases. So you just keep the top K, and you catch maybe 80% of the information you have. But the time complexity is that n has m has k. So, and you also have a very, very large constant here. So actually it runs not fast enough. So before we go to the detail, we want to have a nice theorem. The Johnson-Lindenstrass theorem is called JL theorem. That basically says that if you have n points on a d-dimensional space, so here we have a V here, and we can assume that there's a map on a d-dimensional space data on a k-dimensional space data. K is less than d, so you just map on a high-dimensional data onto a low-dimensional data, such that the distance is kept. So Fu minus Fv, this is the distance. The new distance after projection. So the left and the right side is the original distance. So if the epsilon error term is very small, the distance between the original space and the reduced space is quite similar. Usually the distance is what we care about. We only care about distance between data points. We do not care about the direction or something like the data. So that theory says that if you have n, have d, if you choose k is greater than something 1 minus epsilon square epsilon times the log n, then there is a map f such that for all the u and v, we have the following code. So there is a map such that preserve the distance here. So let's look close to the k term here. So this term is you want to have higher precision. That means you have slower epsilon. You want to have a large k because it's equals to 2 square epsilon. So it makes sense. You want to preserve the distance good. You want to have a large dimensional space you want to project. And the next term is here, it's log n. It's quite interesting. And the more interesting is here, it's not related to the dimension d. It's not related to the how the data point is on the space. That means if you have not so good data points, the initial structure is not too complex. If you're not a very large n, you can choose a very small k here, independent of how the dimension you have. For example, you have 100 of data on a 1,000 space. You can assume that, okay, the data is on a high dimension space, but the structure is quite simple. We can project into a maybe 10-dimensional space. So that is the theorem says. So it's quite interesting. And the second thing is that how to construct FU. So we restrict to a linear transformation. That is, FU is equal to a matrix times a vector. So the thing is how to choose in that matrix. So here is 3 examples. First is R, the random matrix. R, the entries of R has 3 different values. So it's a random matrix. So an entry Rij equal to 0, the probability of that is equal to 2/3. And the probability of an entry equal to +1 is 1/6. And also the next. It's just you have a matrix. You randomly pick up some entries placed by 1, and randomly pick up some by -1, and the rest to be 0. So it's a very simple matrix. And the second is G times S times U. S is a scaling matrix. It's a diagonal matrix. To scale the things is properly scaled. G is a Gaussian matrix. That is, each entry of G is independently dropped from a normal Gauss distribution. So also you can generate such G very easily. Pick up each one from a Gauss distribution independently. And the third one is a structure, has some structures. So it's a D times H times S times U. So S is the same, it's a scale, the rescaling matrix is a diagonal. H is a Hartmann transform matrix. Hope you know that. It is a Fourier transformation on a real space. So you can, if you times this one to H, it has a very fast algorithm. So like FFT. And D is a sampling matrix. That means usually D only stamp K rows from H. So only K entries of D are non-zero, are equals to 1. All the other things are 0. So it makes you just randomly select K rows from that things. So you can reject from D dimensional to K dimensional. So here are 3 examples. As you can see, the structure is very simple. You can just pick up a random matrix, and you can do good approximation. So that is what this theorem says. Okay. Okay, so let's talk about the first basic algorithm we have. So we first construct the M. It's an M times L. random matrix omega. Maybe you can choose it by random, by Gaussian, or by sample automatic matrix. Depends on you. And L is equal to K over epsilon. Epsilon is the error term you want to have. If you want to have small errors, you want to drop a large L, so you have a large random matrix. If you are okay with errors, you can use a very small matrix. Then perform this term. B equals to A times omega. It means project the corner space of A into a random space. Hope that the random matrix omega can catch the corner space of A good. So this is what we mean. And then, so here B is a N times L matrix. L is usually much less than M. So B is quite simple than A. Then we perform a truncated SVD on B. So because B is much smaller now, so the cost is simple. Finally, so assume UK is just the K principal component of B. So now we approximate A just by UK times transpose UK times A. So because UK has only K columns, so this one has only K rows. So it's a rank K approximation. It means that, so the physics means that you project A onto the space of UK and project back. Remember what we have on least square regression? So we project the label onto the sample space and project back and get the estimate labels. So it's exactly the same. So we usually call it the project, orthogonal projector here, this term. So, okay, so good. It's 3 steps. So here is the theory guaranteed. So here is the original A. There's a approximate A. So this is the error between the approximate one and the original one. On the right hand, you have A minus AK. AK is the best rank K approximation of A. So this error is the best you can have. The least you have, you only have if you choosing the K here. So the one we get is just not so bad. Just 1 plus some error term here times the thing here. If epsilon is small enough, we just get the best rank K approximation error. So, but the thing is that if you want to have small approximation error, you want to have a large L here, because L is equal to K over epsilon. And the time complexity is that N times N times log L if you're using Hardeman matrix, because you have very fast multiplication. And it's equal to log L equal to L if you have a Gaussian. But A usually much bigger than K. So if you want to have very good precision, okay, you can use that. You can use a large L, but almost the cases you don't need to very good approximation error. So you can choose in small L. So here's the second one. We have cheaper but less accurate algorithm. So it's the same as remember that the GL theorem said that usually L times K times log K is enough. Why is that? You can do some simple calculation. So maybe you can, log K is quite small usually. Probably K is median. If K is median, log K is it's a 10 or something, larger than A. Okay, so it means that L is usually not quite large than K. So on that algorithm, you just let L equals to K plus a P. P is an oversampling scalar. Usually P is choosing to 5, 10, or a very small constant. So you draw a random matrix, which columns is quite the same as the K, and do the projection. So here's the error bar. So remember that on the previous we have 1 plus epsilon, but now the constant is much larger. So it's 10 times L times minimum of N and M, the square of it. So this constant is much larger than the previous one. But we can have a much less L usually here. So L is the trade-off between approximation error and the computational efficiency. So next we have a cheap but more accurate algorithm. The basic idea is that because you can for matrix A, we just the A to P, A to Q power of the So the basic idea is that you can reiterate several times to improve the space quality. For example, you want to compute the principal component of A, that is the leading singular vector of A. You can use a very simple algorithm. For example, you want to compute the U here. U will be the leading singular vector. You start with a random one, and iteratively compute this equation until it converges. So, and it equals to U equals to A transpose A times A to Q here if you have two iterations.
How do you know it converges?
So here's the old U, here's the new U. If the difference between these two vectors is small, it converges. And you can prove that it converges to optimal solution. So if the difference is quite small, you can have SGD or gradient descent is just iterate, and until the changes are slow, you can stop. So the difference is the precision you have. So approximation error. Yeah. So we can improve the previous algorithm by setting B equals to A times transpose A to Q times A omega here. So this is the actual term here. So why? Why it is the case? Because the singular value of A, so the leading singular value of this matrix is equal to the singular value of the A to 2 times Q plus 1. So if you have, so Q here make the leading singular values, the distance between the leading singular values and the tail singular values apart. So if you have a large singular values and the due power here, and you get a very, very large one. You have a small singular values, and you to Q, you get a very, very small one. So you can separate the matrix. So you can, it's much easier for you to get the column space if you're using just a random approximation. So using that algorithm, you have very high probability everything is improved. By here is the exponential term here. So it's 1 over 4 times Q plus 2. So if we increase Q, this term approximate to 1 exponentially fast. So on practice, a very small Q is enough. And usually we choose in Q equal 2 or 5. It's good enough. And here's the time capacity. The value at this term is quite simple because we can do in the following order. We first A times omega and using transport time. So here is a small matrix now, and then this one is still a large matrix times a small matrix. So it is still good. So the time capacity is just Q times M times M times log L. So it may be double your complexity, but it gives you very good approximation error. So here we have 3 algorithms. So it is the most accurate, but maybe slower. And it is fast, but maybe not accurate. And there's a trade-off. So finally, we get another algorithm we call Nystrom method. The thing is that the previous 2 algorithms, 3 algorithms, want to pass the whole A directory. So you want to pass A several times. So the A is very expensive if A is very large. For example, A is a kernel matrix. You want to compute the kernel matrix, and you compute the whole kernel matrix is quite expensive. If you have a million samples, A is a million by million. If you compute this matrix out, it takes maybe several hours. So the basic idea is that we do not need the whole A here. We just random sampling some columns of A. So here's the neutron method. Assume A is symmetric. It's okay for A is not symmetric, but it makes things simple here. So we just randomly pick up L columns of A to get a P here. And because A is symmetric, so we get a corresponding L columns rows here, and we got a cross small matrix B here. So here is an example. We have A here, we randomly pick up 3 columns here. So because A is symmetric, we have the corresponding 3 rows here, and B is the constant here. B is a 3 by 3 matrix. And so then A can be approximated by P times the inverse of B times transpose P. If you want to have a K approximation error, if you want to have a rank K approximation, you just do a truncate SVD on B. So you get the rank K approximation of B, you get a rank K approximation. So the thing is that you don't need the whole A here. You just a random sampling sometimes. Okay? So why it works? You can see that after reordering, here is the B, here is the inverse of B, and here is the B. So these 3 times equals to B. So at least this part is reserved. And if these columns represent the rest of the columns, it also reserved because it's a spanned column space. So here is the average. Okay?
In practice, how do you do the approximation? It seems that you have to have the A first, you can randomly select the columns and rows to approximate A.
No, usually you do not have the A first. For example, A is a kernel matrix. Each one is computed by 2 sample the kernel distance. If you want to only sample 3 lines, you only compute the 3 columns of the kernel. So you do not need to compute the rest of the one. So it saves a lot of time. And also it saves the space. You only need to compute and store the K columns of the A. So, but it pays because you only sample K columns. The error is guaranteed is much worse. For example, half A is the rank K approximation of the Recitation, and here is the error because it's a random algorithm. It's an expectation here. So the right, you have 2 terms on the right side. The first thing is that the best error you have, the best rank K approximation, plus something you want to pay because you only sample L rows here, columns here. AII star is that maximum diagonal interest for A. If A is a kernel matrix, AII equal to 1. So that is will be 1. So it's not large. So N is the size of the matrix. So L is the how many columns you have. So you increase the number of columns you sample, you get better approximation error. But you increase the computation time. Okay. So far so good. So we have 4 algorithms here. So the first 3, one pass the whole matrix, and this one only sample some columns. And you can have even faster one. Maybe you want to check Alex's talk on fast food on NIPS, this year's NIPS workshop. Yes, using Hardeman matrix to get even faster algorithm because Hardeman matrix has very special structures, makes you compute matrix times matrix very fast. So we do not go that detail. No. Now how we go to the experiment part. So here's the spectrum embedding. So we have hand-write digits. I just sampling 4 digits here, 0, 1, 2, and 9. So we treat each image as a sample. So we compute this similar matrix and compute the kernel matrix, and we do the eigen decomposition of that. We get the best, the leading, the top 2 and 3 eigenvectors and the draw. Using that 2 eigenvectors, draw a figure here. So it's a two, you just reduce the matrix into a two-dimensional space and initialize it. So the first one is that you can perform SVD directly. You can perform replicate SVD here. So, but you want to compute the whole matrix, it's expensive, and you want to store the whole matrix, it's expensive. So we just sampling 8,000 sample here. So it's 8,000 by 8,000 data matrix, and you store it and do a replicate SVD. So it takes you an hour here. And the next thing is that using the whole matrix, whole data set, you have 3 million samples. You randomly pick up 8,000 ones as the column, 8,000 columns of the matrix. You compute 8,000 by 2 millions of the columns and compute the things here. Because you don't need to store on the memory. You can compute on the fly. You compute a small part and do the calculation. So here's the result. So you can see these two are quite similar. The left one is that you have exactly compute the SVD. The right one is that you just sample some data points. You can see that the samples you just sample can preserve the structure very, very well. So it's better embedding. Here is the image segmentation. So here's a fig. So it's a National Geographic fig. There are 2 bears here. And what is image segmentation? Just put image into several parts. For example, you want to put bears into one part, other bears into another part, and the background onto a part. So you can do that by treat each pixel as a sample and compute the similarity between pixels. So if you have, this is about 1 million pixel images, so you compute the kernel matrix is about 1 million times 1 million kernel matrix. And then you compute do PCA, just you compute the leading eigenvectors of that kernel matrix. So if you want to do, for example, 3 segmentation, you want to divide the image into 3 parts. You compute maybe 10 eigenvalues, leading eigenvector of the images, the kernel matrix. So you get 1 billion by 10 low rank approximation of the pixels and run k-means. So you can get a cluster result. So each cluster, because each sample is a pixel, so on the same cluster, the pixels are grouped together. So this is the basic image segmentation tools. So using Recitation method, it takes only 1 second to compute this segmentation. So it's a 1 million by 1 million matrix, compute the eigen decomposition. It's basically, I forgot the number, it's basically 8,000 pixels. I just randomly select 8,000, set the grid of the picture and get a subsample picture, and using that to sample the kernel matrix. So here is more figures. Here has a large figure has 1.8 million pixels. You have complex structures. You can use more segmentations to capture the basic underlying structures. It takes 6 seconds. And here is even more complex figures. You can use more segmentations. It takes more times. It takes about 20 seconds times, but it's well, because it's a very large images. 20 seconds is going to be okay. And finally, the largest picture I could get on 2 years ago is actually it's a picture of my grandparents. So actually, you can do 8 segmentations. It's about 15 million pixels, and it takes 20 seconds here. So you have 15 million by 15 million kernel matrix. You do finding the top maybe 20 eigenvectors, and it costs you only 20 seconds. It's owner modular PC, so it's good. Okay. So conclusion, this works. So it's a basic, very simple algorithms. Maybe you can have a try if you data is very huge, you want to have a very fast algorithm. You can choose that randomized one. It's generally good. Okay. Thanks. Do you have any questions? Okay. We are done.